You know, every so often a paper comes along that doesn't just make things a little bit better, it completely changes the game. Well, back in 2015, two researchers from Google DeepMind, Danilo Rezende and Shakir Mohamed, did exactly that. They gave machine learning a whole new toolkit for understanding complexity and uncertainty. So today, we're diving into their groundbreaking work on variational inference with normalizing flows. Okay, so let's start with the big, fundamental question they were trying to tackle. How in the world do you teach a computer, a machine that fundamentally thinks in ones and zeros, to get its head around the messy, unpredictable, and just plain weird nature of our reality? We're not just talking about telling a cat from a dog. We're talking about modeling the deep, underlying probabilities of, well, everything. And that, my friends, is a monstrously difficult problem. To really appreciate just how brilliant their solution was, we got to go back in time a little bit. See, around 2015, the AI world had this amazing, super popular tool for dealing with probability. The only problem? It had a huge, and I mean huge, flaw that was becoming more obvious by the day. Think about what was happening then. AI models were getting bigger and crazier. We were asking them to do incredible things, like generate photorealistic images or translate languages on the fly. But the methods we had for letting these models handle uncertainty, to basically give them the ability to say, I'm not totally sure about this, they just couldn't keep up. They were way too simple for the complicated world we were asking them to understand. So this go-to tool I mentioned, it's called Variational Inference, or VI for short. And its superpower was that it was fast and it could scale up like nobody's business. It was the absolute workhorse that let researchers train these massive probabilistic models. You can think of VI as the hero of our story. But, every hero has their kryptonite. And this slide right here shows you the problem perfectly. On the left, you've got what a real probability distribution looks like. It's messy, it's got all these different peaks, it's got weird shapes. And on the right, that's what standard VI was using to try and copy it. A simple, boring, single-humped curve. It was like trying to sculpt a detailed statue using only a bowling ball. As the paper points out, this mismatch wasn't just a small error. It led to seriously biased models that were chronically bad at understanding how uncertain they should be. So what do? How do you fix that? Well, the idea that Rezende and Mohamed came up with was just beautiful. Instead of throwing out their simple, fast tools, they asked a different question. What if we could teach a simple shape how to become a complex one? And that is where normalizing flows enter the picture. Now, the name sounds a little intimidating, but the core idea is incredibly intuitive. The best way to think about it is like digital sculpting. You start with a really simple block of clay. That's your basic probability distribution. Then you apply a whole series of very precise, very specific tools to stretch it, bend it, and twist it into something way, way more detailed. The key is that each of these steps is a reversible transformation. Let's actually watch it happen. So we start here with our digital block of clay. This is a standard Gaussian distribution. You've probably seen it before. It's simple, it's symmetric, and for computers, it's super easy to work with. This is our humble beginning. Now we apply our first sculpting tool. It's a specific math function that in this case starts to stretch our simple shape. It pulls it in one direction. And the really critical part here is that this is invertible. We know exactly how to undo this stretch, which is essential for keeping track of all the probability math. And then, with just one more transformation, look at that! Our simple blob has been bent and molded into this crazy, complex horseshoe shape. Now, imagine doing this not just twice, but dozens or even hundreds of times. By chaining all these simple steps together, you can create a final shape that is ridiculously flexible and can actually match the true complexity of real-world data. So what's actually going on under the hood? How does this whole digital sculpting process really work? Let's take a quick peek at the mechanics. The process is basically a recipe. Step 1, you grab your simple starting shape. Step 2, you apply a chain of these invertible transformations, one after the other. Now, each time you do this, you're either swishing or stretching the probability mass around. So, and this is the key, for step 4, you have to be able to precisely calculate how that density is changing. You do that over and over, and what you're left with is an incredibly flexible, complex distribution. Right. Now, here's the secret sauce. This idea of transforming distributions wasn't totally brand new. The real problem, the bottleneck, was that fourth step, calculating the change in density. It involves a bit of math called the Jacobian determinant, and for most transformations, calculating it was a computational nightmare. The cost would grow cubically as your data got bigger, which made it totally impractical for real-world AI.
The absolute genius of this paper was designing clever new transformations, which they called planar flows, that were still really expressive, but, and this is the magic part, they made that calculation possible in linear time. That was the breakthrough that made the whole thing fly.
Okay, so the theory is elegant, the math is clever, but does this thing actually work? Let's see what happened when they put it to the test.
This visual from the paper is just awesome. On the left is that complicated, multi-peaked distribution they wanted to model. And on the right, that's what their model learned using a normalizing flow with just 2 steps. I mean, look at that. It's already starting to capture those different islands of high probability. Compared to that simple blob we saw before, this is a night and day difference in expressive power. And the hard numbers on the classic MNIST dataset tell the exact same story. So their baseline model got a score of about 89.9. For this particular metric, a lower number is better. Now they took that exact same model, didn't change anything else, but just added an 80-step normalizing flow on top. And look what happened. The score dropped all the way to 85.1. That's not just a little tweak, that is a massive improvement. It was proof that the flow-based model had a much, much better grasp of the data. So clearly, this was a seriously powerful new technique. But what about the long run? What kind of impact did this have on the field of AI as a whole? This quote from the paper's conclusion is really the mic drop moment. For years, one of the biggest knocks against variational inference was a theoretical one. Critics said that because its approximations were so simple, it could never, not even with all the data in the world, actually find the true correct answer. What this paper showed was that, in theory, a long enough normalizing flow could. It just completely wiped a major, long-standing criticism right off the board. And the practical legacy? It's just huge. This work directly led to more powerful and realistic generative models. It became a standard, must-have tool for anyone doing serious probabilistic modeling at scale. It gave researchers a unified way to think about all these different methods for getting more flexible models, and it basically kicked off a whole new wave of research into even crazier, more powerful flow architectures, research that's still pushing the boundaries today. At the end of the day, what this paper really did was give AI a brand new set of sculpting tools for the abstract universe of probability. It taught us how to systematically turn simple things into complex things, efficiently. And it leaves you with this one final amazing thought. Now that we can teach machines to flow, what currently impossible shapes, what incredible complexities about our world will they learn to model next?
This is for entertainment purposes only.